So in the previous video, we talked in general about the problem of investigating the responses of LTI systems. And we're going to do that again by looking at a couple of key examples, a first order example and a second order example. And in this video, we'll look at the first order example. The order just refers to the number of poles. It's not only poles that affect the response, zeros do too, but we'll look at the effect of zeros a little while later. And once we've done that, as well as looked at a standard first order and a second order example, we'll be able to extrapolate to more complex transfer functions. So by that point, we'll have a pretty good handle on the relationship between the inputs and outputs of LTI systems. Again, let's look at this standard first order system. So you know how to find the impulse response. The impulse response is just obtained by inverting this transform h of s, which is by definition the transform of the impulse response, though we don't always actually compute them that way. If the input is a unit impulse, then we know that y of s is h of s times 1, the transform of the unit impulse. So we just have to invert the transfer function. Now, of course, this h of s can be rewritten, if we like, into something slightly more familiar. K over tau divided by s plus 1 over tau. So we know that this has a pole at s equals minus 1 over tau. Again, we're assuming that k and tau are positive. Okay. So, in fact, what does the inverse transform look like? You know this. You should probably be able to do this by inspection. It's, of course, also a standard feature of tables of Laplace transforms. This is going to give you k over tau by linearity times the inverse transform of 1 over s plus 1 over tau, and that's just e to the minus t over tau. Okay. So I'm assuming this is a unilateral transform. That's essentially because we talked about various properties of systems, one of which was causality. And it's not hard to see that if an LTI system is causal, then its impulse response is a one-sided function. It is 0, its value is 0 for negative values of t. That just means that the system doesn't respond to the unit impulse delta t before that unit impulse occurs. So a causal system, as defined earlier, naturally has a one-sided impulse response. In other words, h of t equals 0 for all t less than 0. Okay. So we interpreted that transfer function as a unilateral transform and inverted it in the standard way to get this decaying exponential. It has to be decaying because tau is greater than 0. So we can plot this. Sketch it, I should say. So it's going to look something like this. At t equals 0, of course, its value will be k over tau, because the exponential itself will be equal to 1. And then it's going to decay at a rate determined by the value tau. Of course, when t is equal to tau, the exponential will be e to the minus 1, so this will be e to the minus 1 here. When t is equal to 3 times tau, of course the exponential will be e to the minus 3, and conveniently e to the minus 3 is about 5%. So at this stage, the impulse response will have decayed to about 5% of its initial value. So it'll be at 0.05 k over tau, pretty nearly. And I won't draw it here, but when t equals 4 times tau, then e to the minus t over tau is approximately 0.02. So the response is at about 2% of its initial value. So h of t is approximately 0.02 k over tau. That's very useful to keep in mind. After 2 time constants, the exponentials decayed to 5% of its initial value. After 3, about 2%. So this is why tau is called the time constant. It determines the rate of decay. Now, we said that we're particularly interested in the relationship between the positions of the poles on the complex plane and the form of the response of the system. So in this case, the pole is of course at minus 1 over tau. And as we've just seen, tau determines the rate of decay of the response, in particular the rate of decay of the transient response. This impulse response just decays to 0, so the whole thing really is what we would call a transient. And the rate at which it decays is faster the smaller the value of tau. So the smaller the value of tau, the further this pole, minus 1 over tau, is from the imaginary axis. So if we could arrange to move the pole to the left, then that transient would decay faster. If we were to move it to the right, the response would be slower. Everything would play out over a longer time scale because tau would be larger. And this kind of observation is very important, especially when you start designing control systems, as in SE380. A big part of the game of designing controllers is to change the behavior of the system by controlling the locations of the poles. And generally, we want to shift the poles to the left in order to get a faster response from our systems. So this is what the impulse response tells us, the impulse response of our standard first order system. But as I said, we're also interested in the step response, so let's look at the step response as well. Of course, this is very closely related to the impulse response. It's not just a convolution of the impulse response with a unit step, but it's simply the integral of the impulse response. But to find it, we can work in the Laplace domain, multiply h of s by 1 over s, and perform a partial fractions decomposition. That's something that is easily done, and you'll find if you do that, that the result is y of t is k times 1 minus e to the minus t over tau. Okay, so here we have, again, the exponential e to the minus t over tau. So This is again a decaying exponential because tau is positive. So this represents what we would call the transient part of the response. That's just going to go to 0 as t goes to infinity. And then there's a constant part that is going to stick around. That's what we'll be left with in a steady state, as we say, as t goes to infinity. In fact, if you plot this response, it's going to approach the constant value k as t goes to infinity. And it's going to approach it by the same process of exponential decay that we saw in the case of the impulse response. So again, you can gauge the speed according to the number of time constants. And after 3 time constants, you'll be only 5% away from the steady state value. In other words, 95%, if you like, of the convergence will have taken place, and you'll be within 5% of the steady state value. When t is, on the other hand, 4 times the time constant, in that case the step response is approximately 98% of its steady state value. So again, this quantity tau determines the time scale on which things play out, and in particular the speed at which the transient part of the signal decays away, and you're left with the steady state part, which in this case is this step of height k. So it's because k gives you essentially the height of the steady state step. It gives you the steady state value of the response that we call k the DC gain. Because, if you like, it gives the constant part of the response to a constant input, if we think of a step as a constant. Given that we're always going to be dealing with one-sided functions essentially, so a step is what we think of as a constant, or what in electrical engineering you would call a DC, or direct current signal. So we call it the DC gain. As I said earlier, DC gain is a more general concept. And in fact, it applies essentially whenever we can use the final value theorem to find the final value, or the steady state value of the step response. So when can we apply the final value theorem? When all of the poles of your transform lie to the left of the imaginary axis, with the possible exception of a single pole at the origin. Well, if we're computing the step response, we're going to multiply h of s by 1 over s. So that will give us our single pole at the origin. So if all of the poles of h of s lie to the left of the imaginary axis, in other words, their real parts are strictly negative, then we know that we can apply the final value theorem to find the final value of our step response. The final value theorem tells us in particular that that final value will be the limit as s goes to 0 of s times y of s. But in this case, where it's step response, y of s is just h of s times 1 over s. So the s's cancel out, and we're left with h of 0. So in such a case where all of the poles of H lie to the left of the imaginary axis, we call H of 0 the DC gain of the system. So going back to our example, we have H of S equals K over S tau plus 1. So H of 0 equals K. And as we've seen, it's the final value of the step response. That's why we call K the DC gain. Right. There's perhaps one other thing to say about this, the responses of the system. We noted earlier that in general, the step response is simply the integral of the impulse response. In other words, the impulse response is the derivative of the step response. So going back to our little sketch of the step response, we can add a little more information to it. We know that the initial value of the impulse response is K over tau. So that tells us that at t equals 0, the slope, that's meant to be a tangent to this step response, the slope of this step response is going to be K over tau. Again, that's simply because the step response is just the integral of the impulse response. Okay. So I want to stress once again that what we're doing here in particular is studying the relationship between the positions of the poles of a transfer function and the form of the response. In this case, where we simply have a real pole, we have noted that the farther that pole is from the imaginary axis, the faster the response. In particular, the faster the transient part of the response dies away. And the closer it is to the imaginary axis, the slower that response. Why are we so interested in studying the relationship of the response to the positions of the poles? Well, obviously the poles have a large part in determining the form of the response. But to give a more concrete idea of the reason we're interested in this sort of thing, in the next video we'll take a quick look at a simple example of a control system. And we'll talk about how we essentially design control systems sometimes by shifting the positions of poles around on the imaginary plane, and the complex plane rather. So I'll see you in the next lecture.